In this activity, we're going to learn ways to estimate a statistic rather than calculate the true value, which is the parameter. So, years ago, some teacher put this worksheet together of 100 rectangles, and she numbered them from 1 to 100. So the first number does not reflect its size, although it happens to match there. That rectangle has an area of 1. If I go look here, here's rectangle 100. It has an area of 2 because you go 2 times 2, 12, because you go 2 times 6 is 12. And we have all these rectangles here. So I could give you this sheet and say, give me an estimate. And what most of you want to do is do a guesstimate, which is fine. So I went ahead and I said, yeah, give me an estimate and we will record your results. All right. And the answers in the class varied from 6 to 23. And there it was. So these are the dots that we have for the class. We had an average of 12.074. All right. So that you can see there's a 6 and there's a 23. And it was just a quick guess. Now, if I was grading it and you were trying to, and I said, oh, if the closer you are to the actual value, the better your grade. So in this case, I sent them back and they went and I said, pick out 5 rectangles, any 5 you want that think will get you the closest to the true value. All right. So what they did is they basically said, okay, you put down the rectangle number up here. If they did rectangle 1, they put 100. If they did rectangle 100, they'd say 12. So make sure you have the area on the bottom row and the rectangle ID on the top row. Okay. So they added them together and then they wrote their answers down and we captured it on the class dot plot, which looks something like this one right here. Let me scooch up just a touch. So this is the best judgment sample. Okay. So here you can see the values tended to come down a little bit. So we weren't quite as high. And we got as low as 2 and we got as high as 19 on the average, whereas before we were as low as 6 and high as 23. So this would probably be a good guess. 9 is a better guess than 12. All right. So then I said, okay, now we're going to take our brains out of the equation. All right. And we're going to use what's called a random sampling method. So to do a simple random sample, what you do is you number all your individuals. So in this case, we have our rectangles numbered from 1 to 100. And then we use a random number generator to randomly select 5 unique numbers from 1 to 100. Ignore repeats because I don't want to measure rectangle 1 twice. I want 5 different rectangles. That will give me a better chance of getting the true average. So how would we do it? So let me just go ahead and go to random.org. All right. And they basically said, oh, come on, random.org. Where are you? Oh, my goodness. Pause. So here's the website for random.org. And they have a nice little paragraph up here about doing random numbers. So let me go ahead and pull up my calculator. All right. And what I'm going to do, so I already did this before. I already generated some random numbers. This is my captured random numbers from before. And I'm going to go ahead and clear my calculator. So I created these after I cleared my calculator. All right. All right. So you hit the math function, right? And you go to probability. That's where we do random things. All right. And you hit rand and you get a number. Then you do it again. And you get another number. Okay, let's try it again. And we get yet another number. If you compare this list, let's go ahead and blow this puppy up so you can see it better. If you compare this to the list over here, right? It looks very much the same. Well, what's going on, and that's what random.org is trying to tell you, it says the calculators and computer programs are pseudo-random. They try to be random, but they're using an algorithm. So a lot of times the way we fix this in a calculator, we actually go back to the calculator. All right, so let me do a memory clear. Second, 712. So let's say I put in my birthday, April 27th. All right. And then I go ahead and now I hit rand, math, probability, and then rand. Let's see, is that different from my other one? Let's see, where was it? Calculator. Did I get rid of my list? So 0.943597 may or may, it still feels a lot like the other one. So I'm not sure. Let's try another number. Let's do a second. 712. Let's put like pi. All right. And then we hit math random. Ooh, that's still pretty much the same. Yeah. This is why I don't use calculators for randomness. But anyways, so the whole, yeah, see, it's still getting, you see, this is the first number I got. It gave me the same number. This is terrible. So it's not so good. Maybe it needs a bunch of numbers in here so that you can do a better job. I don't know. Math, probability, rand. That's still the same number. Oh, don't use a TI for random numbers. It's not random. Okay, so let me close this. So anyways, the point of random.org is because this problem, that the calculator's not behaving very random, all right? So what random.org does is like, well, you can't use a computer to generate randomness because the computer's going to use an equation. So it takes a measure of atmospheric noise at the moment that you're trying to generate your random numbers, right? And it uses that number as a seed to create another number, all right? And so there you're getting a much better randomization. If you want really good randomization, believe it or not, the best ways to do it are like putting slips of paper in a hat, mixing it up, and drawing, or rolling dice if it's a fair die, or actually flipping a coin. So in the old days, people would actually go do, see if I can find it real quick, random number tables. Before we had all the technology online to do it, people would say, okay, I'll just go ahead and look, this is the National Institute of Standards and Technology. We'll see, my internet seems to be a little bit slow. They actually created these tables of random numbers so that we could say, okay, and maybe you roll a die or flip a coin to decide which line you're doing. And it will, there you go. Here's the official list of random numbers. Boom. So there you go. You could just start. They said these are certified random. Someone was like either rolling a die from 0 to 9. You need to make zeros. And then they just wrote them out. Crazy. All right. So what are we trying to do? We're trying to pick 5 rectangles, right? So I could use integer generator and say, okay, I'm going to do 10 just because I'm trying to show you something. All right. 1 to 100. There we go. Get these numbers. And random.org. My internet's being a little slow. Okay, here you go. Here are the random numbers it generated. Let's see. I don't see any. Oh, wait, look at that. I have 92 twice. So I tend to use a different applet, which is not this one, because you can get repeats. And I don't want to do rectangle 92 twice. I want non-repeating integers. All right. So it's very important when you specify your procedure that you're doing non-repeating integers. So I just need a set of 5 rectangle numbers from 1 to 100. And then I say get sets. This is and there you go. Ooh, that one's working much better. And so it's not going to give me any repeats. If I go back and say, give me 20, right? And I say get sets, there will not be a single repeat in there. So that's how it's programmed. It automatically ignores repeats. Okay, so back to the rectangle activity. You're going, Mrs. Overman, this is taking a while. All right, so we have one set. We make sure we change this number to 5. All right, so let me go ahead and write 5. 5 rectangles, all right? So we're not going to do 10. And 1 to 100, you put your rectangle IDs in the top for rectangle number and then the areas, and you add them up and divide by 5. And I have my students round to the nearest integer just because it's much less messy that way. And this is what they came up with. All right. This is the simple random sample. So if we try to look at all 3 graphs in comparison, all right, The bottom one was the guess, right? So this one is biased, right? Biased high. It was just a guess. But so was this one. This one was also biased high. We favored larger rectangles. All right. Not everybody did. You can see we have a sample that's low and but most our samples tend to be higher than the true mean. So what happened? How do I know it's 7.42? Well, someone actually took a census, measured all the rectangles, added up all the areas, and divided by 100. And they got 7.42 square units. Okay. So that means which sampling method was the best? Simple random sample, because we turned off our brain. So the moral of the story for this is that if you are trying to survey people or anything, if you're picking what you're going to measure and you use your brain, it's a beautiful brain. All right. Your brain might have biases you had no idea it had. How many of you knew that you were sizest when it came to a page of rectangles? All right. And there's probably a couple explanations behind this. First of all, if you've ever heard the phrase, your eyes are bigger than your stomach, you can say, oh, okay, I tend to pick bigger things. But the other thing you look at, if you were to drop a pin on this paper, are you more likely to hit a big rectangle or a small rectangle? The big rectangles are taking up way more area. So if you're trying to land in different places, you're probably going to land on a big rectangle. So there are a couple of reasons. Good news, you do not need rectangle sensitivity training. All right. So sampling bias occurs when one part of the population is favored or ignored. This results in the statistic being over or underestimated. So, I mean, in general, it's going to be over. So for rectangles, we tend to overestimate. All right. Other things you might tend to underestimate. It's just going to depend. All right. And that's pretty much the point of the lesson.